Okay, good afternoon, everyone. We will start our discussions on week 6 content for the course Power System Engineering. So, like the previous sessions, first we'll see the key concepts that will be useful in solving the previous year assignments. After that, we will be solving some questions, and thereafter, we can address your doubts. So, for this week, basically, we will be discussing the concepts for sag and tension. So what is this sag? Basically, let's say you have this conductor which is supported between two towers. So what will happen is, due to the weight of this conductor inherently, instead of being stretched, we can say tightly between this support, it will have some sag, which is represented by the distance d here. So because this conductor is having certain weight, and also because of temperature and other also because of this tension that is acting on this conductor, we'll see after this. So this there is a nature that this conductor will have a sag when it is suspended between such tower. So we need this calculation of sag for designing purposes, because the sag also depends upon temperatures, right? Because this temperature will lead to expansion of the conductor, we can say. So let's say we want to basically have this conductor in certain regions of cold or high extreme temperatures basically. So we need to consider this calculation of sag, basically because suppose this is the ground. So we need that a certain ground clearance we call, let's say this is H. So the H is known as here as ground clearance, because there we have buildings and also human population is here on the ground. So a certain safe distance, we can say, safe distance above which your conductor can be suspended. So that will be basically this height H plus your sag D. So this is required basically for calculating the required ground clearance, also for calculating the height of this tower or pole. Height of this pole or tower, and also for calculating the spacing between this conductor. So for these designing purposes, we need to calculate the sag. Now the stress on the conductor per area, that is stress per unit area, that is calculated as your tension that is acting on the conductor, tension on the conductor divided by its cross sectional area of the conductor. So tension, we measure it in kg, and cross sectional area will be in meter square or cm square. So from this you can calculate the stress on the conductor per unit area. Then second thing was uh, effect of temperature. Basically, whenever there is a increase in temperature, we know that the length of the conductor is going to increase, and as the length of the conductor will increase, the sag is going to increase. And sag and this tension, they are inversely proportional. So sag is going to decrease. So this will happen in your desert. Whereas in hilly or colder regions where there is lower temperature, the conductors are going to contract. So the length will decrease. So the sag will decrease, but there will be high tension acting on the conductors there. So if we calculate the change in length of the conductor with the change in temperature, so that will be delta L will be L naught alpha times delta T, where L naught is your change in temperature. Let's say at temperature T1, your length is L1, and at temperature initial condition T0, your length was L0. So this is at your temperature T0. This is your coefficient of linear expansion that will depend upon the type of the material, and delta T is the change in temperature, that is T1 minus T0. So using this you can calculate how much change in length of the conductor is there due to change in the temperature. Similarly, you can also calculate the change in length of the conductor due to change in tension for a fixed temperature. So this is fixed temperature, here fixed tension. So the change we can calculate it as, here obviously delta is L1 minus L0, and L1 is your length of conductor at tension T1, L0 at tension T0. So this delta T is basically T1 minus T0. M is your modulus of elasticity, that is given in normal in kg meters, and A is your cross-sectional area of the conductor in meters. So whenever there is change in temperature or change in tension, we can calculate the change in length of the conductor using these formulas. Now we'll first see the shape of the conductor. We'll derive the equation for that. So generally what you see, this kind of, so this special shape is known as catenary shape, and we'll derive the equation for this curve. So for that we'll define certain parameters here. So let's say uh, this is your span capital L, and let's say this is your bottommost point. So this D is your sag, right? Maximum sag. So D is your sag, and let's say small L is the length of the conductor. So this is half of the conductor length, so it is L by 2. L is length of conductor, right? So and let's say at certain distance S, so this at point P, let's say we are calculating the tension. So the tension will be acting this way, T, which will have two components, basically Tx and Ty, the horizontal and vertical components. So this uh, horizontal component will be balanced out by this tension H. And we consider that, let's say this is your S length. So this force due to its mass W, where W is this weight per length, right? So W times S. So we consider that it is acting at the midpoint here. So basically S by 2, S by 2. So this is V, and this will be balancing out your vertical component, that is Ty. So if we consider that the sag is, if we consider that sag D is less than, very less than the span length L, then we consider this shape as a parabola. We can take it, simplify it as a parabola. So this is approximation. So now we will derive for catenary curve. So firstly, let's say this hmm, so this we consider a small length ds here, right? Small length ds here. So if I magnify it, so ds along the length of the conductor, this is ds. So this we can break down ds into its vertical and horizontal components, dx and dy, and they are at an angle of theta. So what can I write here? Tan theta. So this theta is similar to this angle theta. So tan theta will be basically dy by dx, or from this upper triangle I can write it as ty by dx, and ty will be same as your v, and tx will be same as your h. This is the relation here. So starting with, I can write this ds square as dx square plus dy square. Basically this vector equivalent of this triangle. So if we divide both sides by dx, so ds by 1 plus dy by dx square. So from here, if I substitute again dy by dx square as this v by h square, so from here I can get dx as basically your ds by square root of 1 plus v by h square, which is same as your ds by, previously we see that v is w into s, where w is conductor weight per unit length, right? So w s divided by h square. Now let us integrate this. So basically your x will be integration of ds by square root of 1 plus ws by h square. So this is sine inverse, and this coefficient of s will come here. So h by w sine hyperbolic inverse ws by h plus your coefficient of constant for this integration. Now if you see the initial condition here, so whenever let's say x is x, if I say this is your x, so if x is 0, that means you are at this point only, right? So whenever x is 0, or this point will move to this point, so then s is also 0, right? So this is for your initial condition. So when x is 0, s is 0, so if you substitute it here, it will give k as 0. So finally we can write x as h by w sine hyperbolic inverse ws by h. So from here we can calculate s as w x h is your sine hyperbolic inverse wsh. So again here we will get h by w sine h wx by h is your s. So this is one of the key relation. So when from here, whenever x is L by 2, so again if you see here, so when x will be L by 2, means you have reached to this point, right? So when x will be L by 2, this is L by 2, then your s will be this whole, right? That is, s will be your length of conductor by 2. So if we substitute that here, your s will be L by 2. So basically you get as L by 2 h by w sine h wl by 2h, or L is 2h by w sine hyperbolic wl by 2h. Now let us see another relation from here. So here we have seen dy by dx is same as your v by h, where v is w times s by h, right? So taking that relation, dy by dx is ws by h, and if you see here, from here this equation you can write ws by h is sine hyperbolic wx by h. Substituting that here is sine hyperbolic wx by h. So you can write dy as sine hyperbolic wx by h dx. So again integrating here, I'll get y as h by w. This will come as cos hyperbolic wx by h plus k1. Now if I see here, we had seen whenever x is 0, so whenever x is 0, so if we consider y as also this point, so basically lowermost point, starting taking that as basically your origin, so you can get y as 0. So substituting that initial condition here, when x is 0, y will be 0. So from here you'll get, so cos will be 1 basically. So k1 will be minus h by w. So this will give our final equation. Y is h by w cos hyperbolic of wx by h minus 1. This was this way. So taking h by w common. So finally this is your this curve equation, that is y in terms of x you got here, y in terms of x. That is the equation of this curve of the conductor, which we tell as catenary curve. So from here, whenever x is L by 2, so we get the maximum sag. Basically here, whenever x is L by 2, so your y will be sag D, right? So y is D, so you will get D as h by w cos hyperbolic of w L by 2h minus 1. Now by substituting the series expansion of cos hyperbolic function, so I'll be getting, that is 1 plus 1 by 2 factorial wl by 2h square. I'm neglecting other higher order terms basically. So I'll be getting h by w, 1 will cancel out, so w square l square 8h, or your d is w square l square by, this is 8h square 8h, right? That is your expression for sag. Now we'll see when it is suspended from tower. So we'll see those parameters. So basically this is your catenary curve, and let's say this distance is capital L, span length, and this is L by 2, length of conductor. So this midway L by 2. So the force tension acting here is H, and let's say this is L by 2. So the midpoint at here we'll get V, that is W into L by 2, and let's say the tension acting here is T, that is having Tx and Ty. So this is your D, just a second. Yeah, so this is your D, and let's say this length is C and this total length is Y. And the angle theta that is making here, so if I extend this, this is your theta that is making with the horizontal. So from here we can see that your Tx is H, Ty is W into L by 2, or we can say W into S. So from total tension we can calculate as H square plus V square, and this H you can write as W times C. So this will come as W times C square plus S square. So from this equation here we can write C as H by W. Now if you remember earlier we had the relation between S here, this one basically. So we'll take that again and write in terms of C. So earlier S was H by W sine hyperbolic Wx by H. So this can be rewritten as your C is H by W. So C times sine hyperbolic X by C. So squaring this here, we'll get S square as C square sine square hyperbolic x by c. And similarly, for y, we had seen y is this relation basically. So y was h by w cos hyperbolic wx by h plus k1. So again, that will come out as y equal to c of cos h x by c plus k1. So if you again substitute x as 0 here, so basically this point, then your y is c, this point. So from that, then you can get k1 as 0. Cos hyperbolic will basically become 1. So y is c cos hyperbolic x by c. And again squaring, you'll get y square equal to c square cos hyperbolic square x by c. So this equation A and B. So let me rewrite that. So S square is c square sine hyperbolic square x by c, and y square is c square cos hyperbolic square x by c. So if I subtract this, so let's say, so y square minus s square I'll be getting as c square, and because this cos square minus sine square have cos hyperbolic square minus sine hyperbolic square, you will get as 1. So from here I can get here y square, or basically y is square root of c square plus s square. And earlier this y was also c plus this distance d, right? This is also equal to c plus d. So from here I can get the relation between, so basically if I square both sides, c squared plus d squared plus 2cd. So c square is gone. So s square minus d square by 2d is c. Now here we have seen this tension here, capital T. So in that we can again write as W into Y, right? So T maximum at the tower support, that is weight into Y. So Y we had seen it is C plus D, or instead of C we can write s square minus d square by 2d plus d. So basically 2d square. So this will be s square plus d square. And t minimum, which will be basically at maximum sag point. So basically this point here, this is your sag maximum, t minimum. So here no ty component is there, right? Ty is 0 and tx is h, which is w times c. So t is tx is wc. This is your t max. So t max minus t min if we do. So t max is this one, w square plus d square by 2d minus this is wc. And c we had calculated in terms of c square minus d square, s square minus d square by 2d w. W will go 2d 2d square, so that will be w times d. So t max minus t min is w times d. If you consider your catenary curve. Now if we approximate that curve as a parabola, so we'll see what changes will be there due to this approximation. Parabolic curve. So for a parabolic curve, basically we take that your d is much less than your L. So basically for your short span line, so we take d, or your sag is very small, and we had seen t max minus t min was w times d, but since d is also small, we take this is small or nearly equal. So similarly, if it is a parabola, so same way, this horizontal force H, and it's a certain point here, Tx, Ty, and this is your T, and this is Wx, considering at a distance x here. So basically you'll get Tx is equal to H and Ty is equal to Wx, and equating the moment at this point, so that will be tension times your y, and here it is Wx times x by 2. So from here I'll get y as Wx squared by 2h, and here we consider T max minus T min small, so basically they don't have any difference. So that is H at this point is equal to H equal to T. Now at X is L by 2, your Y is your D, that is your maximum sag. So D is WL square by 8H, this D. So we can also use this formula for approximation of parabolic curve. The next is in case of unsymmetrical span, that is the conductors they are erected at towers of different height. So basically so this is at a height of, let's say, so let's say this is D2, this is D1, and this is X2, this is X1, and this B H. So earlier you have derived that your Y is Wx squared by 2t. So when at, let's say, D1, Y is D1, so X is X1, so X1 squared by 2t, and whenever Y is D2, X is D2. So this H can be written as D2 minus D1. So D2 minus D1, that will get us W by 2t, X2 square minus X1 square, right? And another relation we have that this is your total span L. So L is X1 plus X2. So from here I can write H is W by 2t. So this is X2 minus X1 into X2 plus X1, this one. So X2 minus X1, and in place of X2 plus X1 we write L. So from here I can get X2 minus X1 as 2HT by WL. And earlier we had seen X2 plus X1 was L. So adding these two we'll get X2 as, so L by 2 plus HT by WL, and X1 will be L by 2 minus HT by WL. So this X2 will always be positive, and this X1 we'll see. So X1 was L by 2 minus HT by WL. So if L by 2 greater than HT by WL, so X1 is positive. This is the case that we saw earlier. If L by 2 greater than H2 by WL, so your X1 will be exactly 0. And if L by 2 is less than HT by WL, this S1 will be negative. So negative means it will lie outside the span. So yeah, so this was your span, right? L. So now your X1 is outside the span, means it will be here. So up to here is L, and X1 is beyond this point X1, and X2 is this, right? So this is your D1 and this is your D2. So this is the case. Now we'll see. Basically, the formula for sag that we got was D is W L squared by 8T. So in case of unequivalent span or unsymmetrical, basically, so you can calculate the equivalent span length for such arrangement. So there are two methods that we have seen, basically. One which is using the concept of average, and another was using this cubic relation. So these are empirical formulas, so you can see that. So in the formula, in place of L, that will be replaced by L equivalent for such a case. Similarly, for W, we have two conditions. Basically, factors affecting W, weight of conductor. So firstly, we have effect of ice. So let's say this was your conductor of diameter D, and then there is ice formation. So we consider that uniformly the ice is surrounding the conductor, that is everywhere it is T thickness of ice is formed on this conductor. So basically this is T, this is also T. So due to this ice formation, basically your cross-sectional area has increased. So if we consider the increase in cross-sectional area due to ice, so that can be written as cross-sectional area due to ice pi by 4 d square. So total ice plus conductor is d plus 2t, and without ice it is d. So if we solve this, we'll get 4t square plus 4 dt. D square is gone, so pi times T also common, pi times T plus D. So this is your increase in cross-sectional area due to ice. So for volume per meter, if you want to calculate this volume of ice per meter length, basically per meter length, so pi t d plus t into 1 basically per 1 meter, basically that will be meter cube per meter, that is volume per meter. And if you wish to calculate weight of ice per meter, that will be basically this pi t into weight of conductor. So this is in kg per meter cube. So kg per meter cube. Finally, this will come in kg per meter. Right. This was in meter cube per meter. So meter cube will cancel out and we'll get kg per meter. So similarly, for effect of wind, so earlier, just a second. I think this is stuck here. Just give me a minute. Yes. So next we were talking about effect of wind. So let's say this is your conductor and your wind is acting on this conductor in this direction. So this is your conductor diameter D. Don't confuse this with sag. Basically, from here onwards, this T is conductor diameter. D conductor. Here also this is D conductor. Okay, I hope this is clear. So now the projected area to the wind, basically F will be A times L. This is per meter length. This is also. And what is the projected? This is D. So D conductor into length, let's say per 1 meter. So this will be your, where this is in meter. So once you get this, from that you can calculate your force. So F force acting will be area times projected area times pressure, wind pressure. Wind pressure in kg per meter square. So basically this will give me D conductor into P, and whole this will come in kg per meter. So let's say if we combine case A and B, that is both wind and ice, so basically this will be due to your W. Just a second. Yes, this is due to wind. This is, here we have initial conductor weight plus weight due to ice that will act vertically, and the resultant effective will be this. So W effective due to wind and ice can be calculated as square plus W conductor plus W ice square. Now, besides this, we have studied about two types of vibrations: aeolian and galloping. So we'll just see how they differ. So the amplitude is less in the range of 0.5 cm, but here amplitude of vibration is more, around 6 meters. So huge difference is there. The frequency of aeolian is more, aeolian vibrations frequency is more, so in the range of 50 to 100 hertz. Here these are low frequency oscillations. Frequency is low, around 0.25 to 2 hertz. So this is due to the vortex phenomena during low wind speed condition. In low wind speed, while this is due to accumulation of ice and this was it. So I think now we can see the questions for the assignment. So first question, temperature increase produces the following effect on transmission line. A, sag and tension of conductor decrease. Sag and tension of conductor increase. This is both decrease, this is both increase. C, sag increases, tension decreases. D is sag decreases, tension increases. So we have seen earlier, yes. So whenever there is rise in temperature, so the conductor will expand, so delta L will increase, or you can say length is going to increase. So that will imply that your sag will increase. And we know sag and tension, they are inversely proportional. So when sag will increase, that is the conductor will now be like this. So that means here tension will decrease. It will be option C. Now coming to question 2. Stringing chart is helpful in knowing factor of safety. Only sag at any temperature. Only tension at any temperature. Both sag and tension at any temperature. So basically stringing charts, they are you can say like a lookup table or chart. It's prepared in offline studies. Offline studies during the planning stage basically. So there you can find the sag and tension versus temperature. So using that you can find this. Now next question. For a span length of 2L, horizontal tension at support is T by 2. Weight of conductor per unit length is W. The value of maximum sag will be, so we know that D is WL square by 80. So L is your span length. So here it is given as 2L and tension is T by 2. Basically 4WL square by 40. That will be WL square by T. This is your answer. Now next question. The sag of the conductors of a transmission line is 3 meter when the span length is 200. If the height of the tower supporting tower is increased by 20%, the sag will be, so if you remember, sag is WL square by 8T. So in this sag formula, so W is your conductor weight per unit length, right? L is length of span, T is your tension. So in this formula, you don't see the height of tower. Height of tower is not present. That means sag is independent of height of supporting tower. So it will remain same. Now next question. Calculate the sag for a span of 250 meter if ultimate tensile strength of the conductor is 6250 kg. Allow a factor of safety of 2, and the weight of the conductor is 800 kg per meter, kg per kilometer basically. So from here, your ultimate tensile strength is given as 6250 kg. So that is your maximum tension that the conductor can withstand. So the working stress or allowable, working tension, I should say, the working tension or allowable tension should be kept below this 6250 by a margin of 2. So it should be operated below its ultimate strength. And here factor of sigma divided by basically, let me write this first. This is your ultimate strength by safety factor. So that will get us 6250 by 2, which is 3125 kg. Right. And rest all thing D is WL squared by 8D. So weight is basically 800 kg per kilometer. So that we can write as by 1000 meter. That will come out as 0.8 kg per meter. So 0.8 L is 250 divided by 8 into 3125. क्योंकि this was in meter, this was in kg, this is in kg per meter. So that comes out as 50 square 2 meters. Now next question. A 132 kV 50 hertz transmission line has weight of conductor as 750 kg per kilometer, span length L as 250 meter, ultimate strength as 3600 kg, safety factor 2, so calculate approx height in meter above ground at which conductor should be supported given minimum ground clearance is 12 meter. So again here W is 750 kg per kilometer or 0.75 kg per meter, and your working stress T is ultimate strength by 2, because that is your safety factor. So that is 1800 kg. So sag is WL square by 80.75 into 250 square, 8 into 1800. This comes out as 3.255 meter. So height H is your ground clearance plus sag, right? Maximum sag. So that is 15.255 meter. Now next question. Again, transmission line with span length 200 meter, conductor diameter as 15 mm, ultimate strength 4500 kg, weight of conductor 850 kg per kilometer, wind pressure P 60 kg per meter square. So calculate max vertical sag. Yeah, so wind pressure 60 kg per meter square. Calculate max vertical sag. If safety factor is 3, assume parabolic shape of conductor. So again here, this is your weight of conductor 850. This will be due to wind, and this will be your effective. So effective weight due to wind, so that we had seen that was pressure times its diameter. So When pressure is 60 kg per meter square, and this is 15 mm. So 15 into 10 to the power minus 3. So that will come out as 0.9 kg per meter. So W effective will be, and this will be basically 0.85 kg per meter. So 0.85 square plus 0.9 square, so 1.24 kg per meter. Again, your working stress or reliable stress will be ultimate strength by safety factor, so 1500 kg per meter. So sag will be W effective square, sorry, WL square by 80. So W effective is 1.24 into span length is 200 into 1500. This will come out as 1.24 into 200 square into 1500. So 4.13 meter. So this is your deflected sag, right? Because in this is your D effective, or we call it as deflected sag. So this again we can break down into its vertical and horizontal. So D horizontal, D vertical. So we can first find out this theta. So let me do it fresh slide. So this is your W wind, W conductor, W effective. This is theta. So this will be your D horizontal, D vertical, and D effective or deflected sag, which we calculated as 4.13. This is 4.13, and weight of conductor was 0.85. Effective was 1.24. So from here, the D vertical, we can write it as, this will be also theta, so as cos theta, and what will be cos theta here? And D effective, that is 4.13, and cos theta will be 0.85 divided by 1.24 from here, right? So we'll get this as 2.3 meter. This is your vertical side. Now question 8. So a transmission line near river crossing is supported by two towers of height 40 meter and 80 meter above water. The horizontal distance between two towers is 200 meter. If the tension of the conductor is 1500 kg, find the clearance in meter between the conductor and the water level at a point at a point midway between the two towers. So weight of conductor is 900 kg per kilometer. Assume parabolic shape. So for this we had seen the relation here, right? This one. First we need to see if this x1 here is positive or negative. So x1 is L by 2 H T by WL. So x1 is L by 2 minus HT by WL. So from here H was, so this H is D2 minus D1, that is difference between height of tower. So H is here 40. L is 200 meters, right? So it will be 100 minus H is 40, tension is 1500, weight is, This will be 0.9 kg per meter, zero point 0.9 into, again the span length is 200. So from here we'll get this as 100 minus negative. So basically this will be the second case, right? So this is your D2, this is your D1, this is 80, D1 is 40, and we need at midpoint, right? So this is L, this is your L by 2, and this is your x1, and this whole is your x2, right? So from here, so x2 minus x1 was 2ht by wl. So this we had seen, and d2 minus d1 was 40, and d2 will be w l2 square for x2 square divided by 2t minus w x1 square divided by 2t w by 2t. So x2 is 200 plus x square, all this we have actually calculated, no need of these. So this x we have already calculated here, right? 233.34. Now x2 was L by 2 plus ht by wl. So that will give us 433.33 meters. So now, if I calculate the sag, so S2 minus S3, that is, or D2 minus D3, D3, yeah, D2 minus D3 is W into X2 square divided by 2T minus W into X1 square divided by 2T. So this will come out as W by T into X2 square minus X1 square. W was 0.9, I think. T 1500. X2 is 433.33. This is 233.33. 0.9 433.33 square minus 233.33 square. So this is 3. So from here you get D3 as D2 minus 23. So this is 80. Now let me insert new slide. This is question 9. An overhead transmission line of a span 250 meter ultimate strength 5000 kg, safety factor 2, if sag is 3 meter, determine weight of conductor in kg. So D is WL square by 80. So T is 5000 by 2, 2500 kg. So W is 8 dt by L square root. That is square root of 8. Sag is 3. This is 2500 divided by L is 250. This will come out as 8 into 3 into 250 by 250. This is 0. Getting it as 0.98. This is in kg per meter. Oh no, so W will be 8 dt by L square. 8 3 2500 divided by L square. So that will come out as 0.96 kg per meter. Now we need to calculate the length of the conductor. So let us check. So from this formula, if you put the series expansion of sine hyperbolic, then you will get the length of the line in terms of span length as L into 1 plus 8 d square divided by 3L square. So L here is 250, 1 plus 8 into 3 square, 3 into 250 square. So this will come out as 1 plus 2 into 9, 3 into 250 square. So this is 250.096 meters. So weight of the conductor in kg will be weight per unit length, that is 0.96 into length of the conductor, that is 240.09216 kg. Now last question. A transmission line having diameter as 20 mm, weight of the conductor as 820 kg per kilometer, span as 250 meter, wind pressure P as 42 kg per meter square, with ice coating of 15 mm, ultimate strength as 7000 kg, safety factor is 2. So calculate maximum sag if weight of ice is given as 19 kg per meter cube. So from here, first we'll find weight of ice. So that will be so this is your conductor DC. This is T. This is T. Yeah. So this is DC. So uniform coating of T, and this is your wind pressure acting P. Right. So weight of ice per unit length you can calculate as pi into weight of ice given, that is 910, into, so volume basically you calculate, and then that will be T into D plus T, right? So basically this formula that we derived here. So pi T D plus T into weight of conductor. So this is your pi into weight of conductor is into T into D plus T. So pi into 910. So mm is converted into meter, and D is, so T basically converting into cm plus 1.5 into again centimeter to meter. So this will come out nearly as 1.501 kg per meter. Now again, due to wind, is wind pressure into dc plus 2t. So wind pressure is 42 kg per meter square. D plus 2 into 1.5 into 10 power minus 2. Basically this mm we are converting into cm, and then again 10 to the power minus 2 we are multiplying for converting into meter. So this will be nearly 2.1 kg per meter. So W effective is W ice plus wind, no, W conductor plus ice plus W wind, because basically wind is in this direction, and this is your W conductor plus W ice, this is your effective. So conductor weight was 820 kg per kilometer or 0.82 kg meter. Ice is 1.5 and wind is 0.8 at 2.1. So this will come out nearly as 3.13 kg per meter. So now your sag is W effective L square by 80. So 3.13 L is 250. Your tension is, so from here tension will be 3500 kg. will come out nearly as 6.99 meters. Okay, this brings us to the end of the session. So we'll close it now.